Welcome to the Deep Dive, the place where we take complex topics and distill them down so you can get smart, fast. Okay, let's unpack this. Today, we're diving headfirst into some truly mind-bending stuff, cutting-edge research that's making us rethink the very foundations of the universe, especially how old it is and the models we use to understand it all. Whether you're looking to impress at your next astrophysics chat, trying to wrap your head around the cosmos, or you're just plain curious about the big questions, this deep dive is packed with surprises. Our guides on this cosmic journey are two fascinating research papers from Ricardo C. Storti. We'll be exploring ideas around cosmological age, this intriguing thing called dark energy redshift, and his comprehensive electrogravitomagnetic, or EGM, construct.
Yeah, and what's really fascinating here is that these papers, they don't just sort of tweak the edges of our current understanding. They go right to the heart of some really persistent problems in cosmology. Storti offers alternative ways of looking at things, ways that could completely change how we see the universe's past, present, and future. We'll be comparing his ideas to the existing standard model of cosmology, the framework most cosmologists use, and pinpointing where he suggests some major revisions are needed.
Right. So let's start with what Storti calls the age problem. Now, the standard model of cosmology, or SMOC, that's the prevailing theory, it uses the cosmic microwave background radiation, the afterglow of the Big Bang, to estimate the age of the universe at about 13.797 billion years. Sounds pretty precise.
Very precise.
But here's the kicker. There's this star called HD 140283, nicknamed Methuselah, and its age is estimated to be around 14.46 billion years.
Yeah, and if you connect this to the bigger picture, you immediately see the puzzle. It's like finding a grandchild who's older than their grandparent. And while there's some wiggle room, some uncertainty in those age estimates.
Sure, always is.
The fact that the star appears older than the universe itself, according to our best measurements, well, it suggests a potential crack in our cosmic timeline. Storti points out that as our measurements get even more accurate, this discrepancy could become, a full-blown crisis in cosmology.
Exactly. And the age of the universe in the SMOC comes from a specific formula.
Yeah.
It takes into account how fast the universe is expanding. That's the Hubble constant, and how much dark energy there is. Now, to simplify things, this formula often uses a value of z equals 0,0v for cosmological redshift when we're talking about the present day.
Yeah.
Think of redshift as like how much the light from distant galaxies has been stretched as the universe expands.
Well, the further away, the more stretched, the higher the z.
Exactly. Higher redshift value.
But this z equals 0 thing, it raises an important question that Storti highlights. Assigning z equals 0 for the present day isn't something we, observe directly. It's more of a convenience setting in our equations.
Okay.
And while it might seem harmless, he challenges us to think about what that assignment really implies about our understanding of the universe. To do this, he looks at an alternative way of thinking about gravity, the polarizable vacuum, or PV model.
Okay, let's unpack this. The PV model. It offers a different perspective on gravity than Einstein's general relativity.
Totally different conceptually, yeah.
So instead of gravity being caused by, the warping of space-time, the PV model suggests it's more like an optical effect, using something called a refractive index, KPV.
Exactly. Like space itself has optical properties that bend light, and that's what we perceive as gravity.
What's really interesting, though, is that even though it's a totally different way of thinking about gravity, the PV model can actually explain all the same gravitational stuff in our solar system that GR does. Things like planet orbits, even black holes.
Right. The Schwarzschild and Reissner-Nordstrom solutions, those key mathematical results, the PV model handles them too. It's isomorphic to GR in those cases.
So it's a powerful alternative framework.
It is. And what's fascinating here is that the PV model gives us a new lens, a new way to look at cosmological redshift. In this model, redshift isn't just about the stretching of light from expansion, it's also related to this refractive index KPV of the vacuum itself.
Okay.
And when we take the standard model's formula for the age of the universe and rewrite it using the PV model's refractive index, well, the equations match up perfectly.
Which makes sense. You said they're equivalent in many ways.
Exactly. It shows consistency.
Here's where it gets really interesting. The PV model reveals a crucial insight about that Z00 value we talked about. According to this framework, a refractive index of KPV OA1, which is what corresponds to z equals 0, could only happen for an observer who could see the entire, possibly infinite universe all at once.
Or someone infinitely far away, yeah. Maybe even outside our universe.
So basically setting z equals 0 for us right here, right now,
Yeah.
it actually describes a non-physical scenario, a calculation step that doesn't match reality.
Precisely. Using 0, 0 essentially assumes we have this godlike infinite view, which directly contradicts what we're trying to do when we observe the cosmic microwave background. We're trying to measure a finite universe. As other researchers have shown, in the PV model's version of Einstein's equations, KPV equals 1 only happens at an infinite distance. It's an asymptotic limit.
So, okay, if z equals 0 is a problem, the next logical step is, what value should we be using for cosmological redshift today?
Good question.
Storti tackles this by considering a universe that has a Hubble radius, RH. Think of the Hubble radius as like a boundary limit.
Yeah, a sort of observational horizon due to expansion. Objects farther away are receding faster than light.
Good.
So if we connect this to the bigger picture, imagine trying to walk around the circumference of a universe defined by this Hubble radius. Storti argues that from our perspective inside this finite universe, the PV model's refractive index needs to account for this limited size. This leads him to define a dark energy refractive index, K.
K lambda.
Yep, K. And it depends on how much dark energy there is, the dark energy density parameter, and the size of the universe within that Hubble radius, the Hubble volume.
Okay, let's unpack this. By plugging this dark energy refractive index into the relationship between redshift and KPV, Storti gets a value for dark energy redshift. And here's a really surprising twist you mentioned.
Yeah, this is wild. For a universe that's expanding at an accelerating rate because of dark energy, this Z actually turns out to be a negative value in the present day.
Negative redshift. How does that even work?
Well, it's a pretty radical departure from how we usually think about redshift. It implies something different about our local space-time environment due to dark energy's influence within that Hubble volume. Furthermore, by combining this dark energy refractive index with the PV model's idea of time dilation.
Time slowing down or speeding up.
Right, depending on the gravitational field, or in this case, the effect of the universe's expansion. Storti comes up with a revised way to calculate the cosmological age, DEAR.
Okay, a new formula for the age. So what happens when we use it?
Well, Storti first considers a theoretical universe of Hubble radius. It's a simplified case where the age of the universe is simply the Hubble time, which is just 1 divided by the Hubble constant, 180.
Okay, age 180.
In this scenario, his calculations give values for the amount of dark energy and for K and Z. And what's really interesting is that the amount of dark energy he calculates is very close to the range the standard model suggests.
So that part matches up, roughly.
It does. And what's fascinating here is that within this theoretical framework, K turns out to be greater than 1, and Z is negative. Both of those results are consistent with a universe that's undergoing accelerated expansion.
So the math works out for acceleration.
It does. This gives us some initial support for the idea that the Hubble age, calculated using this PV-corrected approach, might be the real age of the universe, instead of the slightly younger age we get by setting Z equals 0.
Storti then takes things a step further, right, with a constrained theoretical solution.
Exactly. Here, the idea that the universe's age equals the Hubble time, T0 equals 1h0, is now tied or constrained by the observed temperature of the cosmic microwave background radiation. He uses a specific formula that he and his colleagues developed involving something called the Big Bang Hubble constant and other fundamental constants.
So linking the age directly to the CMB temperature now.
Precisely. And this constrained solution gives a range of possible values for the different cosmological parameters. These are shown in his research in Table 1. What's really remarkable is that quantities like Wa related to dark energy, Wog related to matter, Case, and Ze stay incredibly stable, even when you consider the entire observed range of CMBR temperatures. They barely budge.
Wow, that's stable.
And on top of that, the value he calculates for the present-day Hubble constant, 80, fits right within the range the standard model gives us, but with much higher precision. Much smaller error bars.
Better resolution on AGO.
Yeah, and this strengthens the idea that there's a real connection between the Hubble constant and the CMBR temperature, something scientists expect but, haven't fully nailed down within the SMNU.
Here's where it gets really interesting. The age of the universe that comes out of this constrained solution, it's around 14.5685 billion years. And the margin of error is incredibly small.
14.5685.
That number is strikingly close to the estimated age of that ancient star. HD 140283, Methuselah.
which was about 14.46 billion years, plus or minus zero point 0.8.
Exactly. So this could mean that this whole approach helps resolve that initial age problem we talked about. It potentially avoids that crisis in cosmology.
It certainly brings the numbers into much better alignment, much more comfortable territory. Storti then looks into heuristic solutions too, right? Using SMOC data ranges.
Yeah, heuristic and constrained heuristic. He uses key data ranges from the standard model itself, along with his formula linking CMBR temperature to other parameters. The heuristic solution basically shows that the age calculated by the SMOC doesn't actually line up with the observed CMBR temperature, using his formula.
Ah, another hint that the SMOC age might be off.
Right. But it also shows that the SMOC's values for the Hubble constant and the amount of dark energy are consistent with the CMBR temperature when you use his equation. So it's specifically the age calculation that seems disconnected.
Interesting distinction.
Okay, let's unpack this. The constrained heuristic solution looks at different combinations of the SMOC's dark energy amount and the CMBR temperature. This analysis reveals that while you can find many combinations of SMOC parameters that fit the CMBR temperature requirement, some of the extreme values within the SMOC's accepted range actually contradict other observations, specifically the value of the Hubble constant. Like the upper limit for dark energy doesn't work with the upper limit for HC roll.
There are internal tensions within the SMOC ranges when constrained this way.
Exactly, which leads to a really important discussion. Storti emphasizes the strong link he sees between physical reality and his theoretical universe of Hubble radius.
Which supports the idea that the Hubble age is the true age.
Yeah. He argues that the SMOC's way of determining the universe's age might be off because it doesn't have that clear, direct connection to the CMBR temperature. He suggests the universe's age, its expansion rate, the amount of dark energy, the CMBR temperature, they're all deeply connected. And the SMOC's current explanation doesn't fully tie all those pieces together in the same way.
And that first clue we noticed, the SMOC's age calculation not directly involving CMBR temperature, is made even more significant by the second clue.
The age estimate being younger than that old star.
Right. And while the error bars technically overlap, Storti rightly reminds us, just because the ranges touch doesn't mean the central values are correct. And overlap doesn't resolve the tension if the central values are far apart.
Good point. Error bars don't guarantee correctness.
And what's fascinating here is how Storti explains this difference from the standard model. He pinpoints the assignment of z equals 0 as the likely culprit.
The root cause.
Proposes using the dark energy redshift z as the fix, and quantifies the effect using k. He suggests that the SMOC's simplified age equation, the one usually used, is basically incomplete. It doesn't properly consider the time dilation effects caused by what he believes is a massive photonic field.
Which he equates to the dark energy field itself.
Exactly. He thinks dark energy might be this massive photonic field, and its effect on time needs to be in the age equation.
Here's where it gets really interesting. He even points back to a study from 2008.
Oh, yeah.
Where he and his colleagues apparently accurately calculated the CMBR temperature and predicted the value of the Hubble constant before those values were actually measured experimentally.
Using their formula relating photon mass energy and other constants? Wow. Okay, predicting values that are later confirmed, that's a pretty strong track record. That lends weight to the framework.
Definitely adds credibility.
So this naturally brings us to the second research paper and the electrogravimagnetic, or EGM, construct. This work takes on another really fundamental puzzle in physics. That mind-bogglingly huge difference, like 42 orders of magnitude between the strength of the electrostatic force and the gravitational force.
The many orders of magnitude problem, or MOO. That huge gap.
That's the one. Why is gravity so incredibly weak compared to electromagnetism?
Okay, let's unpack this. The EGM construct. It offers a completely new way of thinking about gravity, doesn't it?
Oh, yeah. Radically different. Instead of seeing it as the curvature of space-time, like in GR, it proposes that gravity is actually a kind of ripple or disturbance in the quantum vacuum, the QV.
The quantum vacuum. Not empty space, but that sort of sea of virtual particles.
Exactly. That seething soup of potential. The EGM construct builds on the polarizable vacuum model we just discussed. It suggests that the curvature of space-time we observe as gravity arises from changes in how this quantum vacuum affects light and other fields its refractive index, that KPV again.
So gravity is like a side effect of the vacuum's properties changing.
In a sense, yes. What's fascinating here is how the EGM construct uses the zero-point field, which is the lowest energy state of this quantum vacuum. This field has a specific distribution of energy across different frequencies, described by a cubic spectral energy density law. It's not uniform.
Okay, cubic law.
And to make sense of all this, the framework uses some sophisticated math tools like Buckingham theory and quantized Fourier distributions, basically ways to break down mass and energy into fundamental vibrations or spectra within the QV.
So it's all about vibrations in the vacuum.
Pretty much. This allows for a connection between Einstein's geometric view of gravity and the quantum world of particles and fields. It tries to bridge that gap.
And the EGM construct has had some pretty impressive successes, right, in explaining things we actually observe.
It has, both at the particle level and cosmologically. For example, in particle physics, it accurately predicts the size, the charge radii, of protons and neutrons.
Their physical size.
Yeah. And the mathematical formula it uses is the same for both, which aligns really well with experimental measurements, including the latest data. That's quite neat.
Okay, that's particle physics. What about the big picture?
Well, if we connect this to the bigger picture, the EGM construct also shows remarkable consistency when we look at astrophysics and cosmology. It helps constrain the properties of the cosmic microwave background radiation in ways that match observation. It might even explain why the James Webb Space Telescope is seeing more early galaxies than our standard models predicted.
Ah, the JWST results.
Exactly. And crucially, remember that 2008 prediction. The EGM construct's prediction of the Hubble constant is very close to the values measured later by the Planck satellite and other methods.
Addressing the Hubble tension again.
Directly. And it even offers a potential solution to the cosmological flatness problem, which is another big mystery about why the universe's geometry seems so finely tuned.
We'll get to that one. But first, here's where it gets really interesting. The EGM construct tackles the MUMAN, that huge force difference. How?
It suggests the gap is related to the different vibrational patterns or frequency spectra within the quantum vacuum associated with electric charge versus mass.
Different vibrations for charge and mass.
Yeah. And a key part of this explanation is the idea of a 90-degree phase difference between how the quantum vacuum responds to electric fields and how it responds to gravitational fields, like they're out of sync.
90 degrees out of phase.
This phase difference, which comes out of the math of the EGM framework, essentially amplifies the difference in strength between the two forces, while still allowing electric charge and mass to be independent properties, which they obviously are.
So it explains the weakness of gravity relative to electromagnetism.
By looking at how these spectral vibrations relate to the accelerations caused by the forces, the EGM construct reveals that the 42 order of magnitude gap is a natural consequence of this cubic frequency ratio and that 90-degree phase shift in the QV. It just falls out of the model.
Wow, so it's not just an arbitrary difference, it's baked into the vacuum's response.
That's the claim. The paper then looks at simplified scenarios at the quantum scale, where that PV refractive index KPV becomes equal to 1. This leads to simpler formulas for the fundamental vibrational frequencies within the quantum vacuum and the maximum frequencies that can exist, cutoff frequencies.
And this helps bridge the quantum and classical worlds.
It helps show the consistency. And as we mentioned, the fact that it derives the same mathematical form for the size of both protons and neutrons is a powerful example of this unification working at the quantum scale.
So the main takeaways from the EGM construct are pretty significant then.
Absolutely. It proposes a way to unify fundamental forces through this phase misalignment and frequency ratio. It suggests a spectral spacetime where gravity as curvature is linked to the QV's refractive properties. It's shown strong agreement with experimental data through its predictions, like for H0 and particle radii, and it provides important cosmological insights, like supporting the Hubble age as the true age, which aligns better with JWST observations of early galaxies.
Okay, now let's dig into the cosmological history of the Moon P. How might that force ratio have changed over time?
Right. Storti maps this out, assuming that the ratio of the electrostatic to gravitational force, let's call it EG, scaled proportionally with the size of the cosmos.
So as the universe grew, the ratio changed.
That's the hypothesis explored here. He defines the very beginning, the Big Bang singularity, and the current state, defined by the Hubble radius, using a set of equations involving fundamental constants like Planck frequency, Hubble constants, etc.
Setting the start and end points.
Yeah. Then, by converting these initial and final states into descriptions based on those QV vibrational frequencies we talked about, the EGM construct establishes a link between these vastly different epochs. This link is then related back to that force ratio, EG, using a scaling factor that connects the present day to these early times.
Here's where it gets really interesting. This framework gives us an equation describing how the force ratio changes as the universe expands.
Mm-hmm.
By solving this equation for the point where the forces have the same strength when Eg equals 1.
Electrogravitational unity.
Right. We can find out how large the universe was and at what incredibly early time this unification occurred.
And the answer is?
A tiny fraction of a second after the Big Bang, during the period we call inflation, extremely early on.
So the forces were unified during inflation, according to this model. Makes sense. The model also allows us to estimate the extremely high temperatures back then. Storti includes diagrams that visually show how the force ratio changes with cosmic size and how CMBR temperature changes with age, giving a nice picture of this evolution.
There's also a table 1 in this second paper that gives a detailed history of this electrogravitational force ratio, predicted by EGM across different eras: inflation, radiation era, matter era, present, future.
A whole timeline for the force ratio.
Yeah. And using another equation, Storti even makes predictions about how this force ratio might change relative to its current value over different timescales, like how much weaker will gravity get compared to electromagnetism in the future.
And what does it predict? Is it measurable?
Well, what's fascinating here is that the predictions suggest we might actually be able to experimentally detect a change in the force ratio in the future.
Really? How soon?
Maybe within the next few thousand to 100,000 years, given how quickly our measurement tech advances. The predicted change over 1 billion years is around -5%.
95%. Okay.
Yeah.
That's potentially detectable eventually. A very long-term experiment.
Definitely not next week's project.
Yeah.
Okay, finally, let's explore the third paper, which directly tackles the Hubble tension using both the EGM construct and the PV model.
Bring it all together.
Exactly. Storti reminds us again of his earlier successful predictions for CMBR temperature and the Hubble constant, which were later confirmed, just reinforcing the credibility.
Setting the stage. So the main goal of this third paper is
To calculate the current values of the standard CDM parameters and describe the entire history of the cosmos in a way that agrees with the standard model where it works.
okay.
But crucially, to show that this apparent Hubble tension, the disagreement between early universe and late universe measurements of age 0, doesn't actually exist within his framework.
Bold claim. So he thinks the tension is an artifact of the standard model itself.
That seems to be the argument. He argues that the fact that general relativity doesn't inherently predict accelerated expansion and can't account for most of the universe's mass suggests it's incomplete at cosmic scales. He uses this really relatable analogy, like relying on a single GPS unit in the vast Siberian forest. It might seem okay, but if it's slightly off, you could be way off course. Relying only on GR might be risky.
So he proposes using, what, 3 GPS units?
Yeah, GR, the PV model, and the EGM construct. By combining insights from all three, he argues that the apparent conflict in data about when acceleration started is resolved.
How so?
Table 1 in this paper shows his calculated values for key parameters at different cosmic ages, and these values seem to align with different data sets, like Freeman's and PDG's, at the appropriate times, suggesting they aren't actually in conflict when viewed through the EGM lens.
Okay, so reconciling different measurements across time, what about the present-day values?
By comparing the EGM predictions with the SOLC for the present day, that's Table 2 Storti points out significant agreement on most parameters, except for the universe's age, as we discussed. The EGM gives that older 14.5 billion year age, but for things like dark energy density, matter density, the numbers are very close.
And he emphasizes that the EGM's adjustments are constrained by the CMBR data, right?
Yes, that's a key constraint. It's not just arbitrary changes.
Then there's the cosmological calendar, Table 3.
Right, a detailed timeline from the Big Bang to the distant future according to EGM. For each major event, inflation, nucleosynthesis, recombination, today, etc., it lists the predicted values for the Hubble constant and the cosmological constant, showing how they evolve.
A full history based on the EGM.
Here's where it gets really interesting. Storti explains how cosmological inflation, that super rapid early expansion, it arises naturally within the EGM construct. It doesn't need to be patched in like it sort of is in the standard model.
It's an organic outcome of the EGM physics.
That's the idea. Figure 2 and Table 4 outline the different phases of this early EGM inflation and this subsequent expansion, showing it as a natural precursor to the later universe.
And crucially, you mentioned the EGM construct doesn't actually require dark energy as a separate thing.
Correct, because the model establishes a direct mathematical link between the CMBR temperature and the Hubble constant value used in TDM. Well, the effects we attribute to dark energy are just inherently part of the EGM framework's description of expansion.
So the accelerated expansion happens, but it doesn't need a separate dark energy field to drive it in this model.
Seems so. The relationship between CMBR and H0 handles it. Storti then presents the core EGM equations and compares parameters like the cosmological constant, density parameters for dark energy and matter, the deceleration parameter, mass density between EGM and SMOC across cosmic history in tables 5 through 9. Lots of comparative data.
Showing the similarities and differences over time.
Right. Then the paper tackles critical density and the flatness problem.
Ah, yes, the flatness puzzle. Why does the universe seem so geometrically flat?
Storti discusses the EGM's prediction for the Hubble constant way back then, refining the moments of maximum temperature and maximum H0. Table 10 compares the critical density calculated using the SMOC formula, but plugging in the EGM's evolving H0 values.
Okay, and table 11 compares the density parameters.
Yeah, the EGM's total density parameter versus the SMOC's density parameter. It shows key differences in their evolution, and points out that the SMOC calculations actually become undefined, mathematically singular, at the moment of maximum cosmological temperature.
Which is a problem for the standard model.
Seems like it. And this leads into the flatness problem, that seemingly incredible fine-tuning needed in the early universe for it to be so close to flat today.
Storti argues the EGM results offer a way out by suggesting the geometry isn't constant, it changes over time.
Which goes against a key SMOC assumption.
Big time.
Okay, let's unpack this. Storti proposes a revised way to think about the density parameters that basically avoids the flatness problem. He suggests the observed flatness is just a temporary present-day approximation. He then lays out the steps using the EGM construct, introducing new concepts like resultant density parameters and cosmological curvature parameters.
Or more parameters.
To describe this evolving geometry. Figure 6 plots these, and tables 12 through 14 show the numbers. Table 15 highlights similarities between EGM and SMOC at different times.
But the key is table 16, right? The curvature history.
Exactly. Table 16 outlines the cosmological curvature according to EGM. It suggests the universe started barely open at the Big Bang,
Okay.
became maximally closed during inflation,
Oh,
and transitioned back to barely open, which looks apparently flat to us today, and is heading towards becoming asymptotically open in the distant future.
So, a dynamic geometry. Never perfectly flat, just passing through a near-flat phase now.
That's the picture. And based on this, Storti concludes the flatness problem, as usually formulated, doesn't actually exist in this framework. It dissolves.
Wow. Okay. That's a major claim.
In the final section, the ideal universe, Storti argues that, look, the standard model was mostly built for the present-day universe. The EGM construct, he suggests, helps fertilize it by providing a more complete cosmic history. He points back to the evidence for EGM's credibility in earlier tables.
And he highlights that there are now two different mathematical solutions, EGM and a modified Espairismo-Astra, that give similar present-day results, but really diverge back at that point of maximum cosmological temperature.
Right. And he introduces another equation, EQUARY 21, for a cosmological curvature parameter,
Oh, yeah.
which he claims is an exact solution from the Big Bang to now, resolving that discontinuity at maximum temperature and staying consistent with other curvature parameters.
Providing a smoother, complete mathematical description.
Yeah, and he concludes the universe is heading towards that asymptotically open state, reinforcing again. The flatness problem isn't really a problem.
Okay, quite a journey through these papers.
Here's where it gets really interesting. So what does this all mean? In this deep dive, we've seen how that seemingly simple assignment, z equal more for redshift today, might be, a fundamental flaw in how we calculate the universe's age.
A potentially incorrect starting assumption.
And the polarizable vacuum model, and especially the electrogravimagnetic construct, they offer some really compelling alternative ways of thinking about gravity, dark energy, how the cosmos evolved.
Frameworks that seem to address multiple problems at once.
Right. And the Hubble age, around 14.5 billion years, as suggested by these frameworks, might actually be the true age, which could solve that puzzle of Methuselah, the star seemingly older than the universe.
Brings things into line.
And on top of that, the Moonpie, that huge force cap, and the flatness problem, two massive, long-standing mysteries in cosmology. They might have potential answers within the EGM construct that tries to tackle it all.
These alternative models, they definitely pose a real challenge to the current standard model of cosmology. It opens up some incredibly exciting new avenues for research. Could lead to a major shift in our fundamental understanding.
Absolutely. And the deep interconnectedness between the age, dark energy, expansion, fundamental forces. It really comes through in this research, doesn't it?
It really emphasizes that these probably aren't separate problems. They're likely different facets of a deeper underlying physics.
And the fact that we might be able to experimentally verify the predicted changes in the electrogravitational force ratio in the future. And that's a tantalizing possibility, right? A way to directly test these ideas eventually.
It is a very long-term prospect, but a concrete prediction nonetheless, which is what you want from a scientific theory. So this leaves us with a final thought for you, the listener, to ponder. How might our entire understanding of the universe shift if these alternative models gain more traction, if they're supported by further evidence?
Yeah, what new questions might arise about the true nature of dark energy, or if it even exists as we think? What about the fabric of space-time itself and those fundamental forces?
If gravity isn't quite what GR says on the largest scales, what does that imply?
So what does this all mean? It means we're at a truly fascinating point in our exploration of the cosmos. Lots of questions, and maybe some surprising new answers emerging. Thank you for taking this deep dive with us. We definitely encourage you to dig into the source material yourself if you're inclined, and really consider the profound implications of these findings.